Hi everyone, my name is Samuel Falvo, and I'm here to talk about a couple of primitives which I thought were kind of neat when I was working on a machine fourth implementation for a RISC-V project that I'm currently working on. And I thought I would share that with you today. It's probably not that groundbreaking, but I'm kind of proud of it, so I thought I would share it. So, what is the problem that I'm trying to solve? Um, Basically, here's an example of a program which accurately represents the current state of the project. And as you can see, it's not terribly elegant. To print the word hello, basically you need to resort primarily with a lot of machine language details. In particular, you need to know which registers to load, you need to know what values to use when making a system call, which you can see here in the emit definition. And really, it's not very forth-like. And part of evolving the machine forth environment to more accurately resemble a forth-like environment, you really need to be able to embed strings. I mean, at the very least for debug messages, right? You want to be able to print, hey, code reached this location. And if I have to do this with, having to break everything out into individual characters, then clearly that's not a very scalable solution. This is great for just demonstrating that the environment runs. But in terms of productivity, it's actually an anti-feature. Right. So what I'm coming up with is now there are some. Before I get there, there are some limitations with the RISC-V architecture. In particular, it lacks any ability to load an immediate value into a register wider than 12 bits in a single instruction. This is not unique to RISC-V, although the width certainly is. Most RISC processors limit you to 16 bits, but RISC-V limits you to 12. Materially speaking, it's not that big of a difference, but nonetheless, if you want to load anything wider than this, you need at least 2 instructions, such as what we can see below with respect to 32 bits. In this particular case, you have an instruction which loads an upper portion of the register, and then you have a second instruction which loads the lower portion. And the reason you might wonder why A, B, C, D, F here instead of A, B, C, D, E like you would expect, it's because that even with Boolean operations, such as or immediate in this particular case, the topmost bit of that immediate field is sign extended. Oh, actually, there's a typo. That should be add immediate. So there you go. So basically what we're doing here is we're treating the upper 20 bits as a separate field, which we know is going to be added to -1 because the high bit of that value there is set to 1. So we know that that's going to be sign extended. Now, when it comes to adding a 64-bit, when it comes to loading a 64-bit immediate value, these tend to be very rare, but they do happen. For example, if you want to access an I/O port, and I/O happens to be located at the top portion of memory, well, there's 2 ways of doing it. One is if it's located at the very top of memory, you can actually rely on the sign extension facility of LUI and ADDI instructions. Or what you can do is if you're just taking an arbitrary pointer to something, you can't really depend on what the 64 bits are laid out or can't rely on any value. The most common thing that you can do is use a constant pool, or some other data structure that stores the 64-bit quantity in memory. So here we have an instruction called AUIPC, which is add upper immediate to program counter, which makes this constant pool location PC relative. So as long as this is within a megabyte or two of the program counter, you can use this instruction to obtain an address of the constant pool as shown here, and then rely on an assigned offset from that to locate a variable within that particular pool. To Intel and Motorola 68K developers, this is probably obtuse, and you're probably scratching your head saying, why would you ever want to use this? On the other hand, if you're coming from other established architectures, especially the mainframe community, this is just the way things are done anyway. So there is prior art to this, so don't freak out over how complicated this is. It is at best an inconvenience, but this is really a solved problem and has been since the 60s. So it just happens that RISC-V is a more modern architecture which does things this way. So how do we get around the inconveniences of this? Well, RISC-V offers a convenient instruction called JAL, and that does two things. One is it performs an unconditional branch to some target location, and it also, at the same time, returns what's called a link address, or return address, really, and it stores that into an arbitrary register of your choice. Now, you'll notice that for X0, I labeled that as an unconditional jump instead of an unconditional call. And the reason for that is, like in most RISC architectures, register 0, or X0, or R0, basically is hardwired to the constant 0. And you may think that that's a waste of a perfectly good register, but in practice it's actually awfully convenient, because it allows you to do things with a much reduced set of instructions than you would expect otherwise. For example, x86 architecture includes a number of separate instructions. For example, test and both perform a bitwise AND on some operands, but test discards the final result, leaving only the flags set, right? Whereas in RISC-V, you can get the same effect by attempting to store the result of a bitwise AND operation in X0 instead of a other register, right? So again, another characteristic of RISC instructions which we can exploit to good use. We use the JAL instruction to skip over some arbitrary size buffer. We have a range of, if I'm not mistaken, plus 2 megabytes and negative 2 megabytes, thereabouts. I don't expect to ever hard code any buffers that size, so I don't bother checking for range in my particular implementation. But if I ever exceed that size, then something is seriously wrong. You should probably reconsider the structure of your program. That being said, it is nonetheless still useful to have inline constants, data structures, that sort of thing, using this approach, right? So what we can do, like in the example here, is we can branch to a forward label that takes about a clock cycle or two, pipeline flushing notwithstanding, and at the same time we're loading register X4 with the quote-unquote return address, if you will, from that instruction. Well, it just so happens to point at the arbitrary data goes here, which conveniently is already 4-byte aligned, because that's useful to know, because most data that you're going to be accessing in RISC-V is going to be 32 bits wide or narrower. 64 bits again will require maybe a different implementation of quote and unquote that guarantees 8-byte alignment, but in this, it's so rarely used that I never bothered to go that far. Forward label then has a or immediate instruction whereby we are setting the register X5 in this case to the size of the data that goes there. So using this particular instruction, what we can do is encode an arbitrary chunk of data up to 2 kilobytes. Why 2 kilobytes? Well, remember that the 12-bit immediate is sign extended, right? So we don't want to exceed 2K because otherwise the result will be negative. And we can easily add checks for that. I just haven't bothered doing it yet because I have no particular need to embed a 4 kilobyte chunk of data inside a single colon definition. But it is doable. It's just, you know, at the moment things are so simple that the 2 kilobyte limitation is what's currently there. The target of the jump and link instruction can itself set a register. Oops, I'm sorry. I actually already explained that. That's a duplicate bullet there. My bad. Okay, moving on. Let's see here. So this is kind of the second half. This is actually what I was going to talk about here. The quote encodes the initial jump and link instruction. You'll notice that it takes a register input. You'll note that if we set that register to 0, like I said, it becomes an unconditional jump, which means that we lose the address of that particular data, and therefore it is semantically equivalent to the henceforth word ahead. I say kinda here because ahead is often used to implement control flow structures such as if then, or begin while repeat, that sort of thing. And those structures are often implemented using conditional branch instructions. The conditional branch instructions on RISC-V have a different instruction format than the unconditional ones do, and correspondingly a much shorter range as well. So for this reason, I separate quote and unquote from ahead and then, with the emphasis that ahead and then be used for conditional branches, whereas quote and unquote use unconditional branches. And it is fully independent. Either way you go, RISC-V uses offsets for everything, which is awesome, because that means that I don't have to restore relocation records. And I don't have to store fix-ups. And certainly don't have to store chains of fix-ups, which is something that often has to be done on x86 and 68K processors. So here's how I implement it. You'll notice that it is an absolute mess of stack permutations and dependencies on the RISC-V assembly, or the RISC-V assembler that I'm currently writing. The quote instruction is the simplest of them because all it does is it just stores a jump and link instruction with an offset of 0. However, at compile time it returns an address to itself. So with that we have what's needed in order to perform the address fix-up, which occurs in unquote. That's what all that messy stack manipulation stuff does there, right? So the first line here calculates I believe that this calculates the size that we need. We align it, we grab our displacement, and then we merge that into the actual instruction itself. That the merge U word here gets its name from the RISC-V instruction formats. The jump and link instruction is considered a U format instruction, and that's where that comes from. Once we're done with that, we then check to see if we have a length to encode. Now, we could just unconditionally emit the OR instruction to load the register, but if the register is 0, it's not going to be used anyway. So I have this if block here that conditionally emits the instruction. So why would you want to use this? I don't know. That's a good question. If you're interested in arbitrary text, we've got established solutions for that. However, if you're interested in other things, quote and unquote really shines, because Here we're showing, like for example, a code quotation in which a word sort vector can call repeatedly as it's doing its business, kind of like how qsort in the C standard library works, where you have this callback which determines the sort criteria for your sorting algorithm. And like I mentioned before, you can also allocate data. So in this case, if I lose access to my global state for my application, I can just call my state, and it will return with a register set in with the global pointer register set to the address of my state. Actually, technically, we're not returning anything there. It's just setting the state of the particular register. And of course, we can use it to implement defer and is. Now, historically, all of these have had their own methods and implementation techniques. But the nice thing with quote and unquote is, at least from my visibility, it provides a nice unified set of primitives with which to implement each of these. So I'm kind of pleased with that. And like I mentioned, ahead and then historically has been used for that in the past, particularly on Intel and Motorola 68K architectures. They can be used to implement defer and is and all the other goodies that we know and love. However, they do not produce any values at runtime, which means that your compiler is more complex if you want to do more tricky things, like, for example, code quotations, right? So your compiler has to pick up the slack, so to speak. You cannot easily depend on state at runtime like you can with a lot of the RISC architectures. So if you're working on the older generation of processors, you might want to stick with ahead and then. That might be a more productive route for you. So anyway, I thought I would give that a shout. It's been a long time since I gave a presentation here at SVFIG, so I thought I would throw this in, and of course it's been a long time since I worked with Forth as well, so this is my first presentation in quite a while. Alrighty, I will end it here, and I will be happy to answer any questions via the SVFIG generalities mailing list, and if I'm online at the time on Zoom, I can answer a couple of questions there as well. Great. Looking forward to talking to you. Thank you very much and appreciate your time.